I think. Yeah, that's on my phone though. So things got a little weird. Hello? Have you guys seen the movie Downsizing?
Yes.
It's really interesting. Well, like, look at me down there. Hey, guys. It's not letting me hit the minus. Oh, well, whatever. It'll be there, I guess. Oh, well. Okay. It's just gonna, I guess it'll just hang out there in the bottom. Okay. Let's see what we can do today. So just like last day, we're just gonna keep trucking through chapter 1 and just kind of get the basics in order, and then we can start some fun stuff. Okay, cool. It looks like it's gonna work, so that's good news. Okay, any questions before we get started? Great. This is just the normal iPad, but it's the new one with the pen.
Oh.
Yeah. But I didn't go pro. Why? I don't need it. Yeah. Adding fractions? You got it. Cool. Yeah, let's do a little bit of review here. Hello. I know. We're all chatty. Last day we talked about bed mass, right? Order of operations. And so we really only covered two main things, bed mass and fractions. So we'll do a little example. Fractions, remember a fraction in general. I need you to remember this terminology. I'll put it over here. A fraction, remember, is a numerator, because it's numero uno on top, over denominator. Okay. And you want to add some fractions, you say. How about we do something like 21 over 4 plus 3 over 61. I don't know. Doesn't matter. All right. Okay. So first step, we have to have them over a common denominator, right? We have to get the same value in the bottom for both of these before we can actually add the numerators together. And then we leave the common denominator the same. So how do we do that? There's lots of ways that we could do it, right? My safest way, and probably the only way that I'll ever do it, is just to cross multiply. Right? So I'm going to multiply both sides by whatever's in the bottom, but over itself. That doesn't really make sense. This side, I'm going to multiply by 61 over 61, right? That's how I get a 61 over here. And then I'm going to multiply this term by 4 over 4, right? What am I actually doing there? I'm actually just multiplying by 1, so nothing's really changing, right? But that's how, and then we have to multiply those, but we can just multiply them, and that's how we get the common denominator, right? So it's going to end up looking like 21 over 4 times 61 over 61, and then separately adding 3 over 61. Oops, not sure what happened there. 3 over 61 times 4 over 4. Technically, just multiplying by 1. I'll put 1 in quotes, right? It is 1. 61 over 61 is 1. 4 over 4 is 1. And we're not changing anything, and that's the key. Okay. But then to multiply these, right, we have to multiply before we can add or subtract. So that stays true, right? So we have to multiply these, and we just multiply across. 21 times 61 stays on the top, and then 4 times 61 is on the bottom. So we have 21 times 61. It's going to be huge. Huge. 1281 over 4 times 61 is 244. Plus, I know 3 times 4, 12. Over, and I know that 61 times 4 is the same as 4 times 61, right? So I already know that it's over 244. Mostly because that was the name of the game, right? Getting that common denominator. Now that we have this common denominator, so we have 244 in the denominator of both of these terms, now we can add them up. But when we're adding, right, we only add the numerators. And then we can put them together. So we get 1281 plus 12 puts us at 1293 over 244. So there are fancier ways that we can do this, but like I said, this is the safest way to do it, and this is the way that I will always do it. You could go through and find common factors and multiply by that and kind of do it fancier, but I just do this. Saves me a little bit of headache later on. No, I would just leave it at that. We could reduce it. I don't really care about that stuff. So 1293 divided by 244 makes 5.299180328. I actually would prefer to see the fraction over the decimal, just because this is less precise than the fraction. So just in general, if you get a nice number, like I think we got 2.75 last day, that's nice, right? Then you can write it out as a decimal, because I know we all like decimals better. I'm sure you do, but it can't just be me. Okay. But so I would just leave it at that. Okay. Wouldn't even bother reducing it. Okay. Mostly because these calculators that we get you to use aren't that good. So, any questions? Like, kind of cool. All right. So, all right. How about, what are we doing today? We're going to start with section 1.4 is on expanding and factoring. I love expanding, and I don't know. I'm okay with factoring. It's not as fun though. A little bit more thinking. So expanding, you probably remember from some point, is if you have something like A times B plus C, right, and I ask you to expand this or simplify this, right, then you would take the A and multiply it by the B. So this would become AB plus, and then you take the A and pull it into the C, right, plus AC. Okay. So this would be your first step, and this is your second step. Okay. Okay. So for example, uh, 4 times A plus 3 right? If I ask you to expand it, then you're going to have, right, 4 times a, so just 4a, plus 4 times 3, if you wanted to go straight to 12, that's okay. But for now, I'll just show what's going on. 4 plus 12. That's good. It's there just for you. It sounds like it's working great. It's good. No, I don't mind. Okay, so what's factoring then? Factoring is expanding in reverse, right? So that means we have to pull a common term outside, right, and put the rest in brackets. So factoring, I think of it as is expanding in reverse. So just working from the example that we were just in, right, 4a plus 12, we see that we have a common multiple of 4 in there. And this is probably why I don't like factoring that much, because sometimes I don't see things, right? I have to actually work through it and see, unless it's very obvious, right? A multiple of 2 or something like that, okay? But we can rewrite this as 4a plus 4 times 3, right? Which means that we have a common multiple of 4 that we can pull outside, and then a plus 3 would have to go on the inside. Right. So because factoring can be a little bit tricky sometimes, right? Whenever I've factored something, especially if I'm not sure of myself, then I like to expand it quickly just to make sure that I got back to the same where I started, right? So whenever I have factored something, I like to expand it to make sure I get back to where I started. To make sure I get back to where I started. Okay. Just as a general rule. Okay. How about if I asked you to factor something like P plus PRT? No numbers in here, right? But we do have 2 P's, right? A P in each, and no other common factors, so that's okay. So we can pull the common P outside, and then inside the brackets, we put whatever the P's are multiplying, right? Perfect. 1, right? Because P is just P times 1, technically, right? And then 1 plus RT. And just so we kind of get in the habit, we don't really need to for this one, but we can expand to check. So P times 1 plus RT, that's going to be P times 1 plus P times RT. That's great. Oh, that's supposed to be a check mark. Just became a slash. Okay. Any questions so far? Okay. So let's do a little example 21. What if I ask you to factor 3b plus ab plus 1 plus t times b? We scan this and we see that that's supposed to be a b. that there's really only one common multiple here, and it's going to be the b, right? So we factor out the b as it is the only common multiple. Oops. Okay. So I'll just rewrite it here. 3b plus ab plus 1 plus t times b. Right, writing b out front, and then everything else in brackets. Right, I have 3 plus a plus 1 plus t. Okay. Just to make sure we can expand to check this. Obviously, if you're working, then the checking it is just for you, right? It's not for marks. Okay. So expand to check it. We have b times 3 plus a plus 1 plus t is 3b plus ab plus 1 plus t times b. I switched the order for the second two terms. Right. And we'll be talking about terms a lot. So this here is a term, right? So each of these little chunks I'm calling terms. Okay. So we're on the same page. Okay. But checks out, it's the same. Okay. So up here, right, I just kept the 1 plus t in brackets because I'd already pulled out the b, so it was nice to just pull it out right away, right? But if you wanted to, then you could expand the b times 1 plus t and then pull out a common factor, right, if you wanted to. So, okay. We kept 1 plus t as it is. But if we didn't keep the brackets, oops. Didn't keep the brackets, right? It would end up looking a little bit different because then we would have 3b plus ab plus, I'll rewrite it here, 1 plus t times b, which would become 3b plus ab plus 1 times b is just b plus t times b. Now we can simplify this a little bit, right? Collect like terms, because we have 3b plus b. Right, 3b and b are like terms. So we get 4b plus ab plus tb. And then from here, we could pull out the common b, right? It would still be the b that's the common factor. Okay. From here, we can factor out the common b. All right, we have 4b plus ab plus tb is b times 4 plus A plus T. Changes our factoring a little bit, right? So recall our earlier factoring was, what was it? Thank you. B times 3 plus A plus 1 plus T. Right. But we look a little closer at this, right? We can just break out the brackets in there, right? Because the brackets around the 1 plus T now aren't actually doing anything. Brackets really only count if you're multiplying or dividing, right? And so we can rewrite this as B times 3 plus A plus 1 plus T. To simplify, we would get B times 4 plus A plus T. And now they're the same. Right. So your answer might not look the same necessarily as your friend if you're working through a problem together, right? But you'll probably be able to rework things and they'll end up being the same thing, right? If you've done it right. If you've both done it right, then you'll have the same answer, just looking a little bit different. Okay, any questions? Oh. Okay. So what if we have to expand something like, what if we have to expand maybe something like A plus, A plus B times C plus D. Well, we have two options. First one would be to treat either of these terms, right, the A plus B term or the C plus D term, as one thing, right? So our first option might be to treat the A plus B as one thing, or one, I guess, variable. Oops. Oh man. So that means that you would have something like A plus B times C plus A plus B again times D. Right? Could do that if you want to. Right? But then you would want to expand one more, right? Bring the C inside the brackets and bring the D inside the brackets. So you get AC plus BC plus AD plus BD. Right? That's one way to do it. Or I'll just throw a note in here. We have two options. First one. The second option is FOIL. First, outside, inside, last, which actually makes no sense to me. I mean, I know how to do it, and it's what I do, but the first, outside, inside, last doesn't make any sense to me. But if it makes sense to you, then that's great. So what does it mean? It means that if you have something like A plus B times C plus D, then you take the A and multiply it by the C. That's your first one, giving you AC. And then you take your A and multiply it by the D. That's your second step, giving you AD. And then once you've done all the, I guess, the A's, right, multiplying A to all the terms, then you move on to your B's and the rest if you have more, right? Then you take B times C, that's your third one, plus BC. And then finally, B times D. It's your fourth term. Plus BD. Bless you. So of course, because we can use either of these ways, right? These yield the same answer, just slightly different order, right? But because we're adding, the order that we add terms in doesn't matter, right? So they're the same. Okay. The first, outside, inside, last. Like I get it. It's like first, outside. Yeah, like for me, I just like to visualize it. And then bing, 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 bing. But there's no acronym for that. Bing, 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 bing. But yeah, and I actually remember thinking about it in high school too. I was like, I get it, but the FOIL thing doesn't really make sense to me.
Well, it's the A and C of the first term, so that
yeah.
And the inside term is the one in the middle, and then the last one is right.
Oh, I get it now. Thank you. It's like learn something new every day. Just a few years too late. That's okay. Great. I guess it only applies to, anyways, if you have 2 and 2. That's okay. As long as you understand. And whichever way you want to do it is fine by me, right? As long as you're showing your work and showing me what you're doing, I don't care, right? If you like the first option, that's great. If you like to do the boing, 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 that's great too. Okay. So let's do a little example 23. Expand and simplify. Expand and simplify x plus y times 3x plus y. Same idea, right? We're just working with variables. That's okay. Oh, I missed an x. Should be 3x plus y. Makes a big difference. So to do this, right, we have to know how to multiply variables and how they behave, right, the coefficients. So this would become, if we just write out exactly like we did with the variables there, just exactly what we're seeing, and then we can simplify it a little bit later. So we would get x times 3x, right, not doing anything to it, plus x times y, plus, now moving on to the y times 3x, plus y times y. Okay. So I'll just make a little side note here. Right, because we need to be able to multiply x times 3x, and because we haven't talked about it, I just want to talk about it briefly. Right? In general, if you have x to the power of a times x to the power of b, simplifying those gets you x to the power of a plus b. Okay. So that means that x to the power of 1, right? X on its own is just x to the power of 1, technically, right? X to the power of 1 times x to the power of 1 is just x to the power of 1 plus 1. So we get x squared, right? Same thing with the y times y is going to make y squared, right? And we'll talk more about power rules as we need them, right? But for now, this is kind of all we need. Yeah. So here, right, this becomes then x times 3x is going to be, I'll pull the 3 out front, and then it's 3 times x, x squared. Right. Oh, is that a question? Fun. Okay, so we have 3x squared plus xy. There's nothing that we can kind of group or do anything with it, so we leave it. Oh, whoops, just xy. And then you'll notice I like to pull my coefficients out front. I like to have them starting all of this stuff, right? So I'm going to pull the 3 out front and then have 3x times y. Mostly because I see that I have another xy term here that I'll be able to combine it with. It's easier to spot if the x and the y are in the same order. They don't have to be, right? And then plus y squared. Great. So this becomes, I'll just highlight our little common terms here. We have 3x squared plus 4xy plus y squared. Okay. Cool. Any questions about that one? Okay. Let's do another one. Example 24. Expand and simplify. Take it up a notch. X minus 2 times 2x squared minus 3x minus 4. Right. Give that a whirl for just a minute. Then we'll go through it together. So as long as we're methodical about it, nothing bad's going to happen. Right? We have a few more terms now. Nothing really changes. Right? So just writing them out in the order that we see them, unless it's super nasty. Then we get x times 2x squared plus x times negative 3x. If you wanted to, well, you could simplify it right away if you wanted to, right? Just do negative 3x squared. You could do that. Or if you want to write the negative 3x first times x, just make it look a little bit nicer, you can do that too. But I'll do this for now. And then plus x times negative 4. Oh, and I guess I ran out of room. Yeah. All my other ones will be minus 2 times 2x squared minus 2 times negative 3x minus 2 times negative 4. Give myself a little bit more room here. Right, so x times 2x squared makes 2x to the 3, right? And then x times negative 3x is going to end up being minus 3x squared. X times negative 4 makes minus 4x, right? Just be really careful with your negatives. You don't want to miss one or lose it somewhere along the way, right? So you have to be really careful. Negative 2 times 2x squared makes negative 4x squared. Negative 2 times negative 3x makes plus 6x. And negative 2 times negative 4 makes plus 8. Now we can collect like terms, right? So we have x squareds go with x squareds and x's go with x's. No other like terms, right? So 2x to the 3, and this one we can probably see negative 3x squared minus 4x squared, right? Perfect. Nice work, guys. And then minus 4x plus 6x. Nice. Great. Notice again, I've just written them in the order of descending powers. We're not going to deal with polynomials. So this is a polynomial, right? When you have x to the 3x squared x, it's a polynomial. We're not going to deal too much with polynomials, but if you're ever finding yourself in a situation where you have to deal with polynomials, then you really have to start writing them in descending order. So it's a good idea to get into the habit, but it's not necessary. Okay, so how about example 2.6? If I ask you to simplify 3y over 1 plus 0.06 in brackets times 175 over 365. Yeah.
Sorry.
Huh?
What happened to example 25?
Oh, we're not doing it.
Oh.
I just pick and choose, yeah.
Okay.
Yeah. But good question. 365, yeah. Sorry, it got a little tiny there. 365. I'm guessing it's days. 175 days out of 365. Okay. All right. So remember, we're going to work the numerator and the denominator separately. There's nothing to do in the numerator, right? But if there was, we can work with them kind of in parallel, right? And so we still have 3y over 1 plus, and we do have brackets, and inside those brackets we have division and multiplication, right? So we get 0.06. It actually doesn't matter the order that we do them, okay? Because, well, we should multiply first, but that means we have to divide. So 0.06 times 175 over technically 1 times 365, right? Why did I do that here? Well, it's because here you could just take 0.06 times this fraction, right? That's fine. But technically we're multiplying two fractions, right? 0.06 over 1. And so if you want to see it, then it's just going to be 0.06 over 1 times 175 over 365. And that's when you smush it together, you get 0.06 times 175 divided by 365. Okay. So I'll just make a note here. Just as a little reminder, we talked about it already, but we deal with the numerator and denominator independently. bless you, until the final simplification. Oops, it says final. Okay. So this becomes 3y, oh, whoops. (3y) over 1 plus 0.0288. Right, just doing 0.06 times 175 divided by 365 is 0.028767123. I've just shortened it. And yeah, we should keep all the decimal places in here. But for this example, I'm not sure we did. Okay, check it. This becomes 3y divided by 1.0288. Yeah. No, I want to see, because it's such a small number, I'd like to see more. Yeah. If you're keeping all of them in your calculator, then okay, right? But because I think, I can't remember, I think we're ditching them, so that's why I wrote them all up. Okay, so we can simplify this right now where we have one term in the numerator, one term in the denominator. Okay. So chatty.
Yeah, I was just gonna say, can we
yeah.
be quiet? It's really distracting.
Yeah,
really distracting.
You don't have to be here.
Just leave, like, honestly, it's really rude.
Thank you. Yeah, I'm sorry to everyone who's quiet. So 3 over 1.0288 times y, that's the same thing, right? So we can rewrite it that way. And then we can finally simplify our term. It becomes 2.916 times y. Any questions? Okay. All right. Let's see. We'll do some real work. First thing. So 1.5 is we're going to start solving systems of equations. Okay, so we have to talk about what systems of equations are and why do we need them, that kind of thing. Okay. In general, it's going to be, so we're only going to be dealing with straight lines, right? And so if you're thinking, you've probably seen a supply and demand curve, right? Something like this. Maybe, maybe not. If you haven't, you will. Okay. So those would be two straight lines and they have equations, right? And so solving these two systems of equations really just means finding the point of intersection. Okay. Why would we care about the point of intersection? Well, because it's the point of equilibrium, right? Especially if we're thinking supply and demand, that's where both parties are happy, right? And so we care about that a lot, especially in business, right? And so solving systems of equations. So in general, I'll just give a quick example here. So a system of equations looks like something like 4x plus 2y is 8. And maybe the other one would be something like 2x minus y is 7. if we're talking straight lines, we're probably used to seeing things in the form y equals mx plus b, right? But it's not that far-fetched to think that we can rearrange either of these equations in the form of y equals mx plus b, right? So if we have an x and a y and that's it, then we have a straight line. It's just different ways of writing it. So in general, if we have two equations, we can solve for two unknowns. Meaning, if for some reason we had three unknowns, we would need at least three equations, right? We can't use two equations to solve for three unknowns. That's just fact. So I'll just make a note here. To solve a system, with three unknowns, we would need three equations. So what I like to do is we would often just number our equations. And if we were to graph these, which we'll move on to probably next day, on an XY axis, just in general, I'm not going to worry about the axes or anything like that. We would have one going up, one going down. Equation 1, equation 2. Potentially, I didn't look too closely. Okay. But so equation 1 would represent the upward one. Equation 2 would represent the downward one. Right? And I'm terrible at supply and demand stuff, so I can never figure out, or I can never remember which one's which, but you guys will know. It's not my job. Okay. So at this point, right, we are at some XY coordinates. So make that a little cleaner. Okay. So solving a system of equations means solving for the point of intersection. There's only one x, one value of x, and one value of y that's going to satisfy both equations at the same time, right? And the point of intersection, is also the equilibrium point. That's why we care about it. Here's where things get a little bit tricky. Not tricky. There are just two common methods of solving these systems of equations. There's one method that I prefer, and I find it gets a little confusing if I show you both ways, and then you have to keep track of which one you're doing. So I'm only going to go through one of the ways. I'll tell you what the other one is. The other one is covered in the textbook. Okay, we'll talk about it briefly, right? If you feel like maybe you would like that one better, then great. Then come talk to me and I can show you how to do it. But I like just having one method. I don't need two methods to do the same thing. Okay. So the first method, my is by substitution. The idea being I pick either of these equations, doesn't matter which one, and I pick one of the variables and I solve for that variable. I just pick whichever one's easiest, and it doesn't matter which of these four I solve for. In this case, I would probably just solve for the y in equation 2. It's already sitting there on its own. I don't have to divide out anything. It's fairly nice to work with. So that's what I would do. So then I have y equals something. Right? We'll go through and do it in a second. And then I would say, okay, well, I know what y is. So then I would plug that back in here in this other equation for y. Right? And then this equation is only in terms of x. That way you can solve for x. And then you can plug that x into y. And then you have your solution. Right? So that's by substitution. By elimination, so the method by elimination would be, you would look at, oh no, okay. It's only because it stops, but I think we're good now. Pretty sure it timed out at the same time yesterday. So it's like, elimination, no. Okay, so elimination would be where you look at each of these and say, what can I multiply or divide one of these by in order to eliminate one of the variables? Okay, so in this case, you want to try to eliminate either the x's or the y's. And so what we would do is we would probably, the easiest way would be to multiply equation 2 by 2, right? Because then I have 4x and 4x. And then I would take equation 1 minus equation 2, right? But I'd have to do it all the way through. So multiplying equation 2 by 2, I would get 4x minus 2y is 14, right? And then I would take this equation minus the new and improved equation down here, right? So then I would have 4x minus 4x, making the x's go on, right? And then I would have 2y minus negative 2y, right? Putting me at 6y is equal to 8 minus 14. Right? Reason I don't like this way, even though it can be a little bit faster, is because there's a lot you have to keep track of, right? And I always forget to multiply this little guy on this end. Right? So kind of more prone to error than I like. Okay? But let's just write out these methods, each of these methods. Okay? So there are two main methods for solving systems of equations. The first one is by substitution. That's where you solve for a variable. Doesn't matter which one. In either of the two equations. Then substitute the result into the other equation. The other equation. Okay. Solve for the other variable. solve for the other variable. And then use the solution to solve for the first variable. I like this method more because it's methodical. Right? Solve for one, put it in, solve for the other, put it in. Your other option is by elimination. And that's where you, oops, take a multiple of one equation and add or subtract to the other, add or subtract it to the other equation. To eliminate, oops, to eliminate one of the variables. Okay. Now you will be left with the one variable which you can solve for, Okay. Then same idea, use that solution to solve for the other variable. Then use that solution to solve for the other variable. So I'll just say, I prefer solving by substitution. And we'll never ask you to do anything by elimination, right? I'll just say, solve the system of equations. And then you can pick whichever method you like, okay? I will ask you to solve a system of equations and you may use whichever method you would like. You will be solving for systems of equations if both on test one and on the final. Okay. So pick a method you like. It's going to bring in some grades. Okay. So let's actually go through and solve 4x plus 2y equals 8. It's that one we started with. 2x minus y equals 7. Okay. So like I said, I like to number my equations. Then I don't have to write them out a bunch of times, right? So in order to show your work, part of showing your work for these problems is going to be telling me what you're going to do, right? Which means you have to use your words, right? So I'm going to say, I'm going to solve for y in equation 2. Not a lot of words, right? But you do have to give me a heads up on what your thinking is, right? You can't just solve for something, right? So just a little blurb like that, solve for y in equation 2, for example, right? Or whichever one you might want to do. Solving for y in equation 1 would be just as easy, right? I probably wouldn't solve for x. Well, in either of those, I'd have to divide. Yuck. Right. So you can just kind of scan the scene, see what looks good. Right. So equation 2 is 2x minus y equal to 7. Okay. Solving for y, I get negative y is 7 minus 2x, right? Moving the 2x to the other side. Okay. And then to ditch the negative on the left-hand side, I'd probably just multiply both sides by negative 1, right? Which means y is negative 7 plus 2x, right? Negative 2 times a negative 1 is plus 2. Great. Okay, so now we know that y is negative 7 plus 2x. Great. So now, my second step, I'm going to substitute y equals negative 7 plus 2x into equation 1, right? We have to do it into equation 1. Putting it back into equation 2 doesn't really make sense, right? We got it out of equation 2, so now we have to put it into equation 1. Equation 1 was what? 4x plus 2y equals 8. Okay. So 4x stays the same. We have 4x plus 2 times y, which is now negative 7 plus 2x equals 8. Okay. We can expand the 2 inside, right? So 4x plus, well, I'll just make it negative right away, right? 2 times negative 7 makes minus 14. And then 2 times 2x makes 4x is 8. Okay. We can combine like terms here. We have 4x plus 4x, putting us at 8x, perfect, minus 14 is 8. Remember, the goal is to solve for x, so we want to get x on its own. So I'm going to move the 14 to the other side, so I get 8x is 8 plus 14. So 8x is what? 22. So x is 22 over 8. Oh, here's that 2.75 I was thinking of. So because 22 over 8, if you check it on your calculator, it does just turn out to be a quick 2.75. And I'm like you, I like decimals, so yeah.
If we just left, we simplified 22 over 8 to 11 over 4 and left as a fraction.
Oh yeah, that's great. Yeah, more work than I'm expecting to see, but yeah. Hey, that's always better, right? So now we know that x has to be 2.75. So now we can just substitute that back in to solve for y, right? So use, oops. Use x equal to 2.75 to solve for y. we already solved that y must be -7 plus 2x from earlier, right? And so y must be -7 plus 2 times 2.75, making y is -7 plus 5.5, or if you wanted to skip straight to -1.5, that's fine by me. Okay. Therefore, the solution to this system is x equal to 2.75 and y equal to -1.1 or -1.5. Or we can just write, oops, sorry. 2.75 -1. Right, just coordinate notation is fine too. Okay. So that's saying that both these equations have to be true when x is 2.75 and y is -1.5. Right, so we can actually, what's nice about these problems is once you've done all this work, right, it is a lot of work, then you can actually just check your answers and make sure that you're right. Right, so it's a good idea to check your answers. Okay. It's always a good idea to check your answers. All right, so equation 1 was 4x plus 2y. We want to know, does it equal to 8? So I just put a little question mark over the equal sign. So does 4 times 2.75 plus 2 times -1.5, does it equal 8? 11 plus -3 is in fact 8. Awesome. We can check the second equation too, since we're on a roll. 2x minus y, does it equal 7? 2 times 2.75 minus -1.5, does it equal 7? So 5.5 plus 1.5 does equal 7. Great. Okay. So that's what's nice about these problems is you can check your answers. Okay. Any questions about that one? I have a bit more work. It's pretty fun to get the hang of things. Okay. How about we do another example, example 28. If I ask you to solve 2x plus y is 4, and x plus 1/2 y equals 2. Calling this equation 1 and this equation 2. Okay. I think I would solve for y in equation 1. It's sitting there all on its own and positive. It's nice, right? So solve for y in equation 1. But like I said, whichever one you choose, there's no wrong pick here. Just some are easier than others. Okay. So we have 2x plus y equals 4. solving for y, right, we just have to move the 2x to the other side, so we get y is 4 minus 2x. Great. So now we want to substitute y equals 4 minus 2x into equation 2. Right? We got it out of equation 1, so we need to put it into equation 2. Okay. So then equation 2, right, is x plus 1/2 y is 2. So x stays the same. X plus 1/2 times 4 minus 2x is 2. Okay. So then we can bring the 1/2 inside. X plus 4 divided by 2 is 2, right? Minus 2 divided by 2 is just 1, so 2 minus x equals 2. Okay. Now these brackets aren't doing anything, right? But when we try to simplify this here, right, we get x minus x, right? So we really just end up with 2 equals 2. That's true, right? But what does that mean in terms of our system? It means that it doesn't matter what x is, 2 will always be 2, right? And so you could put in any value of x, and if you get a statement like 2 equals 2, then that means that you have an infinite number of solutions. Okay? So, because it doesn't matter, 2 is always going to be 2, and that's true. So, okay. So, as 2 equals 2 is a true statement, I think we can all get on board with that. Oops. That doesn't specify what x is. Specify what x is. We have an infinite number of solutions. An infinite number of solutions. If you work through in a similar scenario, right, and so you get to the end here and somehow your x's cancel or your y's cancel, depending on what you're trying to solve for, right, and you get to a false statement, that can happen too, right, where you see something like 0 equals 2, right, that's never true, meaning there are no solutions, right? So these are the two special cases where you either have infinite solutions or absolutely no solutions, right? So in a similar scenario, okay, if you get to, I'll call it the end, right? You get to, you're very close to solving for x, but then you get to the end, just kind of flats out, right? Then, so the end, and find a false statement. Okay. Like 0 equals 2. That means that there are no solutions, right? No solutions to that system. Okay. So those are two special cases that we kind of have to keep an eye out for. Infinite number of solutions or just no solutions at all. But most often we'll just be able to find a solution and that'll be it. Any questions about that? Yeah?
We cannot find the value of y.
No. No, then you're done.
So all we have to do is write down that there is no specific solution.
Yeah.
And that's the end of it.
Yeah, if that's on a test, that is the test question, right? Do you recognize that when you get there, you either have infinite solutions or no solutions? Yeah, that's good. Cool. Any other questions before we move on? Okay, so section 1.6 is on ratios, proportions, and percentages. Okay. So a lot of the time in business, right, we have percentages that we have to deal with, taxes, you're out shopping or restauranting, you're tipping, right, that kind of stuff. You can take it outside if you want. Okay, I don't care. Okay, so we're going to be dealing a lot with percentages. One main thing that we have to keep in mind is that to work with percentages in math, right, we have to reduce it to the decimal form or a proportion, right? So a proportion is a percentage, it's just the decimal version, right? And so I'll just make a note here. To use percentages, right, 15%, 7%, that kind of thing, in calculations, we need to use the decimal form. Okay. So a proportion is just a fraction. Okay. Often written in decimal form. And takes on values between 0 and 1. Okay. So a percentage divided by 100, right? Oops, I say 100, but I write 10, is a proportion. 15 as a decimal, we have to divide by 100, makes a proportion, right? 0.015.
So all of these things are going to be representing the same type of
basically, yeah.
Just in a different form.
Yeah, yeah. We'll talk just a smidge about ratios right now, and then I don't really think we need to waste our time on them. Okay. So where did I I want to steal. I want to steal this. So I didn't start writing in there. I was kind of hoping you guys wouldn't notice. So it's a little tiny, but I'll read it to you. So I think this is a really funny blurb from the textbook because it's all official, but it's really just talking about peanut butter sandwiches. Suppose that there are 2 goods required to make a good sandwich: peanut butter and bread. We know that it takes 4 spoonfuls of peanut butter to cover 3 slices of bread. So the ratio of peanut butter to bread is 4 to 3. Okay. Then suppose that we have 75 slices of bread. How many spoonfuls of peanut butter should we have? There's lots of ways that we can solve this, right? And whatever comes to you naturally, that's the way that you should stick with, okay? So if it doesn't come to you in the way that I'm gonna solve it, that's fine, right? As long as you get to the same answer, then you're good, okay? And for that reason, I don't wanna talk too much about ratios because we're already pretty good at solving these things, just kind of manhandling it, right? We can kind of figure it out, right? Sometimes we can't even explain how we found it. We just know, right? So, but how I'm gonna solve it is I'm gonna say, okay, well, they're saying that there is some peanut butter to bread slice ratio, right? And the ideal ratio is 4 spoonfuls per 3 slices, right? They don't have to be in the same units as long as you're talking about the same units all the way across in your numerator and the same units all the way across in your denominator, right? Spoonfuls over slices. Okay. So then the problem is if we have now 75 slices of bread, right? How many spoonfuls of peanut butter do we need? Right? So now we have this, well, these 2 fractions we can work with, right? And so I'm going to focus on just the last 2. The first one I just set up so I could look at the setup, right? How do I want to lay these out? Peanut butter per slices, right? So 4 over 3 is x over 75. Solving for x, right? All I have to do is multiply the 75 over. Right? And so I get 75 times 4 over 3 is x. And because I like to have x on the left-hand side, I'm just going to seamlessly do a switcheroo here. So we need 100 spoonfuls. Okay. But like I said, the reason I don't want to talk too much about ratios, if you're having troubles with them, then definitely, come talk to me. But we have kind of developed ways to deal with problems like that already in our head. Right? Okay. So let's talk more percentages. So taxes are pretty common, taxes and tips. Pretty common examples of percentages. Right? And so I'm going back into garbage and I'm stealing another thing. Now that I'm busted, I'll just call it what it is. So last time I ate out, my bill was $45 before 7% tax and a 15% tip on the bill after tax. How much did my night out cost me? It's a reasonable question, right? We're going to deal with this in 2 phases. Right, first I'm going to figure out, okay, so my bill was 45, and then we have to figure out what the bill was with tax, right? Because we're told that we're tipping after tax. Right? So I'm going to set this up as the cost, which is before the tip, what? Oh yeah, makes sense. I was thinking taxes. It's a cost after taxes, but before the tip. Is going to be the price of the meal, right? The $45 plus the tax. Okay. The price of the meal is, we said $45. I'll throw in a $sign in there. I'll probably forget about it later. till the end. Plus 7% tax, right? If we want 7% of 45, that's really just $45 times 7% as a decimal, right? 0.07. Good. I'll just make a little note here. 7% tax is 0.07. Okay. So we could do this, or we could start recognizing the pattern of the common multiple, right, of 45. So we could start writing this as 45 times 1 plus 0.07. All right, I've just pulled out a common multiple of 45. Okay. And that's why usually if I tell you, okay, your bill is $45 and you have to pay 7% taxes on that, if you want to know the total, then you just take 45 times 1.07. Right? You probably use that in the store all the time, right? But this is why, the common multiple. Okay. So you have 45 times 1.07. Making $48.15. Okay. So that's the cost after tax, right? And then we're going to tip 15% on top of that, right? So the total cost is going to be the cost plus the tip. Cost plus the tip has the same setup as the cost plus the, or the price plus the taxes, right? So we have 48.15, oops, 15, plus the tip, which is 48.15 times 0.15, right? 15% of 48.15. I'll skip a step here and say 48.15 times 1.15. $55.37. So at the end of the day or the end of the night, it sounds like you'd have to pay $55.37. Right. How about another scenario where we kind of have to work backwards a little bit? It's a little bit more fun. Okay. So a local pub has offered a $10 dinner. So all you pay as a customer is $10, right? But they're saying that's going to include your 9% tax and a 15% tip, so you can feel good about yourself after tax. Okay. So what is the cost of this dinner that the pub is actually serving you, right? So what would be the equivalent of them advertising a price and then you paying 9% taxes and 15% tip after taxes, right? To get you to $10. So we're basically gonna work backwards, right? Because we're given that the total cost is $10, right? So we're gonna undo the tip and then we're gonna undo the taxes to find out what that original price is, right? So we're told that the total cost, oops, I did it again. The total cost is $10, which is the cost after tax plus the tip. Okay. So 10 is going to be, I'll just call it C, the cost. times 1.15, right? 15% tip. Just going back to here, right? We said, okay, well, we had the costs after taxes times, and then to get the total amount with the tip, right, we just multiply it by 1.15. So even though we don't know the costs yet, we're trying to solve for it. We can solve for C, right, by dividing both sides by 1.15. So we get, and I'm going to put the C on this side, 10 over 1.15. Divided by 1.15. So the cost after tax is 8.6956. So 870. Right? They would round to pennies. If you had kept all the decimal places, that's good, right? I don't mind that, right? Even though they would round to pennies, right? Because it's money. Okay, so then the cost or the price is the cost plus the taxes. Right. The price is before tax and tip, and the cost is, what did we say, after tax? Oh, I mixed those up. I did. Yeah, I'll just, sorry guys. I mixed those up. So the cost, you always have the bigger one on the left. The cost, which is still after tax, is going to be the price plus the taxes. That makes more sense. And the cost was 870, and the price, we'll call it P, times the taxes, I think there were 9% in this case, so 1.09. So P is going to be 870 divided by 1.09. Puts us at a price of $7.98. Once we've rounded. Cool. Any questions? Yeah.
Neither of these gave us the number, what the actual cost, what the actual tax is, and it's
Yeah, because we have to find it.
okay.
Yeah, but yeah, cool. Yeah, they'll only be given in percentages.
Okay.
Yeah, cool. Any other questions? Yeah.
In a question like this, will we ever have to figure out what they're gaining?
Maybe like way later this term. Yeah, it'll be like, it won't be until like mortgages where it's like, how much did you pay in interest, that kind of thing. So no, that'd be way too evolved. Anything else? Any other questions? Yeah.
It shows you the tip after you find out the cost. So that's important.
Yeah. This type of question, working backwards, I don't think I would do that too, right? It's just good to see it that we can do it, right? Might make you do it on a homework problem or something like that. But on a test, no, it would be kind of like the first one, where I give you something and then you have to pay taxes and then you have to tip on it, right? Which I think is kind of easier to deal with. Right? Does that make sense? Any other questions? Cool. All right. Well, I'll see you Tuesday. Crazy. Have a good weekend, I guess. Yeah. Oh, did anyone not get a schedule yet? Yeah, come and get it. We'll just be here. Sorry. Just in the textbook. Yeah, they're all fine. Yeah. So if you want to work through the whole textbook, you can.